Hello everybody and welcome to Simple Harmonic Motion Lesson 6. Now in the last video where we looked at maximum values in SHM, where the maximum displacement value by definition was the amplitude. The maximum velocity value was omega multiplied by the amplitude, and remember that omega is 2 pi over t, or obviously 2 pi f if you do know the frequency, but 2 pi over t will be, at least with SHM systems, an easier one to calculate and an easier one to work out. The maximum acceleration was omega squared multiplied by the amplitude. After the maximum values, we then looked at energy, and finally in the last lesson we derived the general velocity equation, which was V is plus or minus omega multiplied by the square root of a squared, the amplitude squared, multiplied by the displacement squared. Now, so far in this topic, in the first 5 videos, we've completely ignored any resistive forces that are acting on the SHM systems. So that might be air resistance or friction, or those kind of things that are going to act to oppose the motion. Therefore, in this video, we're going to move on and we're going to have a look at what this means, adding these resistive forces in and the effect that it has on the motion in SHM. If therefore we go back to the mass on spring system, now when I originally recorded this, I've done about 2 minutes worth of recording. Now if we have a look at where the mass gets down to at the negative amplitude position, I know we've got a little bit of parallax error on this, but we can clearly see that it's going down to below where the clamp stand is. Now if we just wait for a moment or so, we will start to see the effect of damping. But first we can start to think about what resistive forces are acting on this system. Well, firstly, there will be at least a little bit of air resistance acting on the masses themselves. They're a flat surface as they go up and down, and therefore a little bit of air resistance which will be opposing that motion. The second force that we're likely to have is also a little bit of friction in the spring itself. As we extend and compress the spring, there is friction between all the molecules in the spring, or the different bits of the spring, which will obviously therefore dissipate, probably is a little bit of heat, and therefore we've got some form of resistive force there. Now, while I've been talking, we can already see that the masses are now, at least again with our point of view on this system, they're not extending down past the bottom of the clamp stand. They're pretty much level with the clamp stand at this point. And if we just watch a little bit longer, we can see that in fact we're getting to the stage where they're not even coming down level with the clamp stand, or just about. They're kind of above the clamp stand itself. Now as I alluded to during the video that we just watched, the collective term for these resistive forces, at least when we're applying them to an SHM system, we call them damping forces, and the overall effect is therefore known as damping. Now if we think about this for a moment, when the system was moving up, and this is regardless of whether it's above or below the equilibrium position. We don't really, at least for this bit, we're not really interested in whether it's above or below equilibrium. We're only interested at the moment in the direction of the velocity. Now when it was moving up, the force would have been acting down. It would have been acting in the opposite direction. And conversely, when the system was moving down, the resistive force would have been acting up in the opposite direction. So firstly, when we're looking at damping forces, we can see that the damping force, and we'll just use F with a subscript D, that the damping force will always oppose the velocity. So it will act in the opposite direction to the direction the system is moving in at any particular time. Secondly, if we go back to year one, when we looked at drag as part of the kinematics topic and the kinematics videos there, when we looked at drag, we saw that that drag force was proportional to the velocity, and in fact it was proportional to the velocity squared. As I said, that little bit of information we need to see year one kinematics for. Now, when we combine these two ideas together, we end up with a little bit of a cyclic argument. The effect that the damping force has on the velocity is that it will act to decrease it because it's acting in the opposite direction. But so that's the effect of number one. But as V decreases, because the damping force is proportional to V or proportional to V squared, then V will also end up decreasing the amount of damping force we've got. So as one decreases the other decreases the first one, and we keep on going round in a bit of a circle. We see this kind of cyclic argument in other areas of the course as well. If we think about nuclear physics and look at nuclear decay, we see that the rate of decay, dn by dt, is proportional to minus n. So the decay rate depends on the number of nuclei that you've got remaining, but of course that is constantly decreasing anyway, and therefore that's decreasing the rate itself, and the two are therefore related to each other. We get a very similar situation there. We end up then, if you go back to the nuclear physics topic and have a look at that, we end up with the equation n is equal to n naught e to the minus lambda t. In other words, we end up with an exponential decrease in the number of nuclei that we've got. We also see the same in capacitors as well, where you might look at the charge on left on the capacitor, and that delta Q by delta T, which is of course the current, is proportional to the charge that is remaining on the capacitor, and that's decreasing as well, and from that we end up with the equation Q is equal to Q naught E to the minus T over RC. But the point is, once again, we end up with some form of exponential decrease in something. So when we bring this back to SHM then, we can see that we've got to have an exponential decrease in something, and we can hopefully see that that exponential decrease will occur in the velocity. Now, of course, because the exponential decrease occurs in the velocity, and we know that velocity is a derivative of the displacement, we can hopefully see that the displacement will also exponentially decrease, or at least the amplitude will exponentially decrease as well. So now then, let's try to plot a graph to see how this is going to work. So we'll do a graph of displacement against time. Now each of these will represent one time period, so t, 2t, 3t, etc. Firstly then, I'm just going to draw our exponential decay in, something like that. So there then, at least either side of the axis is an exponential decay, and we call this the exponential envelope. this, of course, is our positive amplitude position and negative amplitude position. So when we have the effect of damping, the amplitude, the maximum displacement that we get from the equilibrium position, will decay exponentially, as we saw back on the last slide. Now, we're not actually going to go into trying to derive an equation for this, because it does get a little bit more complicated and goes beyond what we need to do at A level. Obviously, if you go on to university level to look at this kind of stuff, then you will start to derive equations. But as long as we know that it's an exponential envelope, then that's all we really need to know for this video. Now, the exponential envelope is very similar to the envelope that we had when we looked at waves, and especially when we looked at the double slit pattern for waves and for interference. In other words, the system will still oscillate, but the displacement from the equilibrium position will never go outside that envelope. When it comes to time period, though, let's just remind ourselves of the equations we've got. Firstly, for simple pendulum, t equals 2 pi root L over G. And then for mass on spring, which is t is equal to 2 pi root m over k. Now, well, when we look at these two equations, obviously the 2 pi's in both equations are just numbers, they're therefore constant. For the simple pendulum, the length is a constant, and g being the acceleration due to gravity. Well, as long as you don't move the pendulum while it's undergoing damping, that will also be a constant as well. Exactly the same goes for the mass on spring. The mass doesn't change due to damping, that's a constant. And then when it comes to the spring constant, well, the clue's in the title there, it's a constant as well. What we see then is that for both equations, everything that we have on the right hand side, they're all constants, and therefore that means that the time periods must also be constant as well. When we translate that onto the graph then, because the time period is a constant, if we start at positive A, then after one time period we'll be back at positive A, and so on. So whenever we have the time periods, we're always going to be at the positive amplitude position. Obviously, therefore, at half time periods, we will be at the negative amplitude position. So I'm just putting those on to help me to draw this. What we end up with then is a graph that's going to look like this, if you excuse the drawing close enough. These are obviously supposed to be aiming for the crosses. There we go, that's better. So we can see the time period is remaining the same, or at least as close as I can draw it using the graphics pad, but that amplitude decays exponentially and obviously will go on and on and on. Now, that style of damping we call light damping. In other words, light damping, when those resistive forces are relatively small, they're going to be smaller than the force that's actually causing the system to move in simple harmonic motion in the first place. Now, of course, if the previous example was known as light damping, which is the damping that's going to happen to the vast majority of SHM systems that we care about, then obviously the opposite of light damping is going to be heavy damping. Now, heavy damping occurs when any damping forces that are acting on the system are very large, where the forces that are acting are larger than the forces that are keeping the system moving, in theory, in simple harmonic motion in the first place. Just to give you a sort of silly example, if we were to take a simple pendulum or a mass on spring, and instead of having it oscillating in air with very low resistive forces, very low damping forces, if we instead put it into something like treacle or golden syrup or something like that, something with a very high viscosity, then that's going to give a very large damping force. Now, if we do have heavy damping, then we're going to get no oscillations at all. Okay, because there simply isn't enough force in the system to overcome the force of damping in the first place. What we will though get, again, if we have a graph of displacement against time, we will just get a nice slow exponential return to equilibrium eventually. Okay, so the system will return to equilibrium. So it obviously will eventually, because it will need to, if it's not in equilibrium, there are still forces acting on it, so it will still go back to equilibrium, but it will take a long time to do that. So we've looked at the two extremes there. We've looked at light damping, where we have very low damping forces acting, and we've looked at heavy damping, where we have very large forces acting. Now, in between that, at the crossover between the two, we find critical damping. Now, if we draw the graph again, x against t, critical damping occurs when the system returns to equilibrium as quickly as possible without any oscillations occurring. So we can say that the system, key points are, returns to equilibrium in the shortest possible time, but we have crucially no oscillations occurring. Now, critical damping is crucial, especially from an engineering point of view. You'd probably be surprised when you sit back and think about it, how many times you do see critical damping occurring. Firstly, if we look at automotive, from the automotive engineering point of view, if you look at cars and motorbikes, and depending on how sort of how technical your push bike, your road bike, but mountain bikes especially are going to be, you find critical damping systems on them, and they're known as shock absorbers. Obviously, when you're looking at a car, we know full well that the roads that we drive on in cars are not completely flat. There are obviously bumps in the road and potholes and all this kind of stuff. Now, when we go over one of these bumps, at the four corners of a car we have springs. They're known as suspension. When we go over a bump then, those springs will compress. As soon as you've got compressed springs and you let them go, well, they act as a mass on a spring system, and you should in theory get oscillations. But of course, in cars you have shock absorbers, so that when the springs compress and then extend again, we don't want them to oscillate. Obviously, if that happens, what you would see is cars bouncing down the road, and we simply don't see that. Cars go over bumps, the springs compress, and then the shock absorbers stop them from extending too far and going into oscillations. Now, there are loads and loads of different places that you can find critical damping, and what I suggest you do, maybe as an exercise for yourself, is go away and just search for uses of critical damping systems, and have a look at the different places and the different situations where you might find critical damping occurring. Now, of course, that is the theoretical version of how critical damping works, and obviously we cannot always have that theoretical view of it. In reality though, again, bearing in mind that we're talking about engineering, manufacturing, all that kind of stuff, it's very difficult to engineer or manufacture something to do a job 100% perfectly. In reality, with a lot of critical damping systems, they will get to equilibrium but will normally just shoot past and then very quickly come back to the equilibrium position. So in reality, we will get a little bit of oscillation. That's why you do feel some bumps in your car when you drive over them. But realistically, they're going to come back to equilibrium very quickly, and we're not going to get massive oscillations that you would normally get when you're dealing with any kind of light damping system. So to summarise this lesson then, we've looked at damping and we've looked at the three different types of damping that can occur in an SHM system. Firstly, for light damping, we saw that the amplitude decays or decreases exponentially. But that the time period remains constant. For heavy damping, so where we have large damping forces, bigger than any forces acting in the SHM system, that it will simply return to equilibrium very slowly. And then for critical damping, we get a fast return, okay, in the shortest possible time, to equilibrium. So that's it for this lesson. I hope you got something positive out of that and now have a good idea of how damping works. I'll see you in the next video.